Break this down into cases, x being between -1 and 0, x being greater than 0, inducting in both instances. That works perfectly well, just a little longer than it needs to be. Questions on this one? Yep.
If it wasn't a fixed value, would you have plugged in like an extra?
Yeah, if the problem were stated as for all x in the real, or for all x greater than -1, and for all, that might be a little bit more challenging. What we typically would do there, and I'll come over here as a reminder, back when we first saw quantified statements, you know, for all x, p of x, if we wanted to show this, our technique was to pick an arbitrary x. So in that case, we would pick an arbitrary x and then show, you know, what we'd be looking at would be something along the lines of this. Or maybe put it this way: for all x greater than -1, for all n an element of the naturals, p of xn, where p of xn is this statement with x's and n's in it. We would pick an arbitrary x, and so in other words, fixing it, and then induct on the rest of it. Did that answer your question? Others? All right. Number 8. I think number 8, where problems came up on number 8, where people were making this problem harder than it needed to be, thinking that it was asking for something more than it is asking for. Perhaps because maybe you were all worried about the, you know, showing it's an equivalence relation when there's modulus things in there. Notice in the statement there, we're not asked to show it's an equivalence relation. We're just asked to work with modular numbers here. Okay? This one is, remember I told you I shortened up a problem and I took off a problem? Well, this is the shortened one. Right? I made it into an easier version of what it was originally. Originally there was, show it's an equivalence relation and blah, blah, blah. And I tried to make it a little easier by just saying, assume one thing about modulars, show another thing about modulars. And so real quickly, if A is equivalent to B mod n, then A squared is equivalent to B squared mod n. There are a number of ways to go about this. I think there were at least 3 different that I remember approaches to this particular argument. We make our assumption here. Since A equivalent to B mod n, we have k an integer such that A minus B is nk. That's what it means for A to be equivalent to B mod n, that their difference is a multiple of n. And then, what we want to do is we want to show that A squared minus B squared is also a multiple of n. A squared minus B squared. Here's the easy way. The difference of 2 squares can be factored easily. There's something we know about. A plus B and k. N times A plus B k. There's an integer. A squared minus B squared is an integer multiple of n. Boom. A number of people did things like solve this for A and inserted it in here. And when you do, you solve this for A, you're going to get nk plus b. When you square that, you'll get a b squared term out. And it will cancel with this b squared term. Everything else will have an n in it that you can factor out. A couple of people, 2, maybe 3, solved this for A and solved it for B. And then put in the one for A and the one for B. What happens when you do that, however, is you end up with an A squared minus B squared left in it. Right? Or actually, a B squared minus A squared left in it. And that tends to cause a few little problems to it. If you just do it with one of them, things work out nicely. If you do it with both of them, it gets a bit messy. You can get there eventually. It just will be, you know, another half board or so of work to get there. Like I said, I intended it to be easy. I think people made it harder than it obviously is. Yes?
Would this one be able to be done with induction, because it's for let n be greater than 2, so isn't that implying anything greater than 2?
While we could do it with induction, it turns out that so if we think about our inductive process, right? Base case, n equals 1, say. Assume the n equals k case, and then show the n equals k plus 1 case. That's sort of our basic induction process. To show this case doesn't at all depend on any of this. The process to do it doesn't depend on the above. So you don't need the induction. Could you do it inductive-wise? Yeah, but you don't end up needing anything above there. It makes it a whole lot more challenging than need be.
So because it's not like recursively defined, I guess?
Yeah, I guess maybe that's the way to think about it. That it's certainly there isn't a recursive aspect to the question, to the statement. It is. I mean, like I said, it could be. You could attack it with induction, but the argument is going to be to argue this right here is going to be the exact same as without it. So it's what's the right word here? It's kind of superfluous. It's added extra stuff that's not needed. Back over here, right? Universally quantified statements. We can prove them by just fixing an n and showing it's true for that n. Okay? This one is hard to do that way. Fix an n and try to show it for that fixed n. It's hard to do. We really need, I've erased it now, but we really need that extra information that this assumption gives us to prove it. That's where the induction is really needed. In this case, we don't need that information.
I think I just saw the let n be greater.
I can see that. Lastly, problem number 9. As I mentioned on Monday, I put problem 9 on there as sort of a, okay, let's give you a new definition, something you haven't seen before, and see if you can work with it. Let's just put it this way, it didn't go all that well. Right? I mean, I'm sorry about that. So let's take a look at it. So, assume R is reflexive and circular. And just as a quick reminder up on the board, you guys all have it by you, circular. If AB is in R, and BC is in R. So notice that's an if. Then CA is in R. This doesn't imply in any way, shape, or form that AB and BC are in R. They might not be. For example, real quickly, separate from this, that relation is reflexive, everything's got a loop, and it's circular. Anytime you get both of these satisfied, the only way to do that with these would be AA and AA, then AA. Yeah, okay, it works, right? And so most people that started to have problems on this one, because there were a few blanks, the ones that were long, I guess, thought the exam was long. Most people that had this one that were having problems with it made assumptions about AB and BC being in there. And we don't know that necessarily. It's an if they're there, it's a hypothetical. So, we want to show R is symmetric. So what does it mean to be symmetric? If AB is in R, then BA is in R. That's what it's meaning. And so now, if we're going to show this statement, Here's a conditional statement we wish to show. We get to assume the hypothesis and come up with the conclusion. And notice, it's that assumption of the hypothesis. There's where all of a sudden we get the AB being in R. Not over here. While this is true, it doesn't mean we have to have anything there. Now all of a sudden we get something there. So let A be an element of R. Excuse me. Then, by reflexive property, we have B be an element of R. We know it's reflexive, so we had, like in the picture I had here, everything's got a loop, right? So now we've got AB and BB. We've got AB, oops, AB and BB. That tells us that BA must be an R by the circular property. So by circular property, BA an element of R. We're treating, in essence, we're treating this like a C over here. And so this gets treated like a C here as well. If it'll make those confused faces I saw, let me change this from A's, B's that you have over there to X's and Y's. Anytime we have two ordered pairs in the relation where the second coordinate of one and the first coordinate of the other match up, then we can get out of it the second coordinate of the one, comma, the first coordinate of the second. And so that's what we've done here. X would be A, Y would be B, Z would be also B. And so then we get Z comma A, or B comma A. Right. So like I said, this one is meant sort of as that sort of little challenge. How far can we go beyond it? And like I said, I'm not overly disappointed with the problem. I think the length of the exam affected the results on it. By the time you got to it, you didn't have time to think your way through it like you could have. And for that, I apologize. Like I said, I'll adjust scores in the end. I think that's the easiest way. Typically, by the way, just because I know there's some in the educational track here, typically what I would do in this kind of a situation where we have that big spread of scores but still some way up at the top scores, is I'd have you redo part of the exam. Take two problems and redo them for more points. Our issue is, we're on the last day of class. We don't really have enough time for you guys to go out and do that again and come back and have it be meaningful. Doing that allows you to actually, if you will, learn from those mistakes. And we don't really have that time right now. Had this been the first exam where we had this score range, I would have done that. I think in the end here, we'll just adjust scores as needed. All right, so I know it took up a majority of our time, but I wanted to make sure we went through all of the problems on the exam. If you want to discuss the results of the exam, I'm certainly more than willing to do that, but let's do that individually rather than as a group setting. Also, add up your points, make sure they're adding up properly. If they're not, let me know, right, so that I can adjust things. But those get added up in my head, and I have been known to make mistakes in the adding. The rest of our time, though, let's make sure we're talking about the final, which is Monday afternoon. Right? Monday at 1 instead of at noon, so you get to sleep in a little extra. Right? I won't be around Monday morning unless you want to interrupt me because I'll be in this room at that time with the other exam that I'm giving on that day. Right? You can do that. Come here and get my attention through the door or come on in. We can step out in the hall and have, if you have questions, have a brief conversation. More important or more likely to occur would be tomorrow during reading day. I'll be done with my morning commitment probably by about 11. So from 11 till 2:30 to 3, I'll be around my office. And then on Friday, from like 8:30 in the morning till 2:30 to 3 in the afternoon, I'll be in my office for office hours. Any of that time. After that, I'll try to on Sunday in the late afternoon to early evening, check email. So if you have an email question, you can send it that way. I intentionally keep personal email and work email separate. I don't have it linked to my phone or anything like that. That's so that I can keep sanity in my life. So I have to